This video considers mixed programming and linkage constraints. Mixed programming is when you have variables that are binary. Binary variables can only take the value 0 and 1, right? Binary. Typically, we're used to continuous variables, something like money is continuous, weight is continuous, temperature is continuous. With 0 and 1 variables, you either do it or you don't do it. And we're going to bring that into our examples to try to model fixed cost. So this is the 5th video in a series of 5 videos. We started out with constrained optimization, just a very, very simple example. And then we went to linear programming, where you can have more than one decision variables, right? You can have more than 2, 3, 4, 5, 7 decision variables. And you can also have constraints. So in linear programming, all the functions are linear. It's the constraints that make it difficult, right? And so modeling those constraints and learning to manage around those constraints are very important. What we're going to do tonight is take a look at the linkage constraints with mixed programming to try to model fixed costs. Okay, so what is a binary variable? Well, it just takes 2 values, 0 and 1, okay? Really simple, right? However, it leads to a lot of technical difficulties. So there's been a lot of research on how you actually find the optimum when you have 0 and 1 variables. It turns out to be extremely hard kind of mathematical problem. It's much simpler if you have a continuous variable because your functions have jumps in them. And when you have a jump, you just have to find all possible combinations to see where that jump is and then evaluate it. Whereas with calculus, when you have continuous variables, you can say, hey, if I increase x by a little bit, I know that y will increase by a little bit. I don't have to worry about jumps. So the real advantage, though, of using binary variables with optimization is you can bring in logical conditions. Like if condition A holds, then we do x, otherwise do y. And we'll see how that works out. So we're going to go back to our example with Half-Baked Bakery, where we're making cookies and cakes and trying to maximize our profits. But we have the typical constraints on production capacity. But now we're trying to figure out how we can model in fixed cost. How can we bring in fixed cost? So what's a fixed cost? A fixed cost is a cost you incur regardless of how much you produce, right? So whether or not you produce, a tenth of a pound or 1,000 pounds of cookies, you still have the fixed cost. And often the fixed cost is things like setup costs, right? You have to set up your production line to make cookies. You have to set up your production line to make cake. If you're not going to make cookies, you don't set up the production line, so you don't have the fixed cost. If you make even a tiny bit of cookies, you have to set it up and you still have the fixed cost. Same thing for cake. If you make no cake, no fixed cost. If you make some cake, regardless of how much, you still have that same setup, the same fixed cost. This is also sunk cost because, hey, if you don't make anything, if you went through the setup, but you decide, hey, I don't want to make it, you still have it. So not a good thing. So here's how the Half-Baked Bakery example gets modified. We still let x be the pounds of cookies and y be the pounds of cake. We're going to introduce 2 binary variables, f of x and f of y. And the way we will use that is f of x is 0 if x is 0, and f of x is 1 if x is bigger than 0. Okay, so we have some logic going on here. Same thing for f of y. This is to pick up the fixed cost. If y is 0, then f of y is 0, and f of y is 1, then y can be bigger than 0. We have the same marginal profits as we had in the previous video, 20 cents for each pound of cookies, 30 cents for each pound of cake. But now we introduced a fixed cost. If we make any cookies at all, we have a fixed cost of $30, right? And if we make any cake at all, we have a fixed cost of $75. And so we come up here with the objective function. So we get the contribution for making cookies and cakes, right? 0.2x plus 0.3y, just like we had in the previous videos. But now we subtract off those fixed costs, right? So this objective function is profit. And of course, if you think about profit, you subtract off the cost. So 30 times fx minus 75 fy. So if you just look at the logic of it, if we're making both cookies and cakes, then we have what we earn, the net income or the marginal profit for making cookies and profit for making cakes. But now we have to subtract off the setup costs for cookies and cakes. So f of x is 1, f of y is 1, and so we end up subtracting off 105. If we don't make any cookies and we just make all cake, then of course we only have the marginal contribution of the cake we're making, but then we have to subtract off $75 for the fixed cost of cake. If we're making cookies but no cake, it's just the opposite, 0.2x minus 30 f of x. And then if we don't make either, then of course profit is 0, right? Don't do anything, you don't make any money. All right. And we have the same production capacity constraints as before, where we have a mixing operation and we have 210 hours of mixing. Cookies and cakes consume the same amount of the mixing constraint. Baking, we have ovens with 250 hours of oven time, and each pound of cookies consumes a quarter hour of baking, and each pound of cookies consumes a quarter hour of baking time, and each pound of cake consumes a half hour of baking time. And then we have an icing operation, which is just for cake, and we have a total of 80 hours of icing. So those are the same production capacity constraints we had before. Okay, so let's try to just set this up. Let me just go to Solver and try to set this up. And I call it and just let's see what happens. So I have to get over to Excel. And I have some of the Excel functions set up all right. This is what we had before. We have the objective function. We have cookies and cakes, pounds of cookies, pounds of cake, contribution for cookies, contribution for cake. And now we put in the fixed cost. So we have the fixed cost when we're doing cookies, our f of x, and then we have the cake, f of y. In this starting value, we have making 10 pounds of cookies, no pounds of cake, so we'd like to make this 1 and this 0. And then the fixed costs are actually minus $30. Oops. Minus $30 if we make cookies. And for cake, it's minus 75. And then the total profit, again, is just our sum product, which is our friend. We highlight the decision variables. We put F4 down. And then we highlight the contributions, the constants for the profit function. No stars around it. I'm sorry, no dollar signs around it, and just there you go. So if we make 10 pounds of cookies, we lose $28. But we're not making too much here, but we have that big fixed cost. Okay, and now we can bring this on down to the. Oops, what happened? How much we used and what's our capacity. Sorry about that. Okay. And what do we have? We have the capacity for mixing is 210. Capacity for baking is 250. Capacity for icing is 80. Okay, just like we had before, and we're going to be less than or equal to. Okay. Now, in Excel, blanks are the same as 0, but I'll just go ahead and put the zeros in just to indicate I'm not doing anything there. Well, I put them in the wrong spot. Just move them over. And now I copy and paste this down. Control-C down to here. Control-V. Okay. Wonderful. So I changed the amount of cookies I have, change the profits and so on. Let me just check to verify that I have the right things selected. 11 times 0 plus 0 times 0.2, 1 times 0, 0 times 0. Yep, looks like it's all right. Okay, so now we want to set up solver. Okay, so that's our objective function is F3, and we bring solver into action, and data solver, way tidy. No, not J4. Let me go total profit. What do we want to change? We want to change these decision variables. Okay. Now we have the constraints. So we want to add these constraints in, our capacity constraints. Okay. All right. And then we want to make sure my fx and fy are binary. And if I don't do anything at this point, they will not be binary. So what I need to do is say add. I'm going to add some more constraints. I highlight the decision variables here. I come to the drop-down tab, and I select binary, B-I-N for binary. It'll say binary there. You click OK, that's great. Okay, so there's my objective function is F3. I have the binary constraints on D2 and E2, and then I have the capacity constraints on the operations as we had in the previous video. Okay, now there's something different we have to do. This is no longer a linear programming. We can't use the simplex algorithm. So let's just use GRG nonlinear. Okay, and then you just say, we're set to go. Okay, just say solve, keep your fingers crossed. And what's happened here? Okay, got a solution. We're making 400 pounds of cookies, 300 pounds of cake for a total profit of $170. Okay. Mixing is binding, baking is binding, and icing is slack. We got the same solution as we did with the linear programming. What's gone wrong? Something's gone wrong. Well, look at these. Look at this. We're making cookies and we're making cake, but solver forces fx to 0 and fy to 0. And why did it do that? Well, because if fx is 1, you get a minus 30, and if fy is 1, you get a minus 75. You lose money. We're trying to maximize, so we don't want to lose money. So solver says, hey, you didn't give me any kind of constraint on what f of x and f of y is, so I'll just set it to 0. Okay, so it's saying, hey, I'm going to allow you to make cookies and cake, but you won't be picking up the fixed cost. Well, and when I first did this kind of problem a number of years ago, it kind of blew my mind. It was like, whoa, what happened there? And then how do you come up with a solution? Okay, so let me just go back to the slides, PowerPoint slides. And okay. This is just the naive model we just set up. Well, I have a little bit fancier formatting for you all. And so what's wrong? You know, we have these zeros in here. So what do we have to do? Well, what we didn't do is we're not coordinating my X and Y with my fixed cost. There's nothing in the model that forces me to pick up those fixed costs, right? It says, hey, nothing in the model that forces me to eat those fixed costs. It's like, hey, it's free. No worries. What we'd like to do is like put if then else statements in it, right? So if you know a little bit about Excel, you could put if X is bigger than 0, then we have the 30. If X is equal to 0, we have a 0. Okay. If Y is bigger than 0, then we pick up 75. If Y turns out to be equal to 0, it will be 0. Except for solver doesn't like this. Okay. If you try to put this in, put this logic into the objective function, solver will say, no, you can't do it. You can't do it. So someone a little bit more clever than me came up with these linkage constraints, and they're really, really cool. When I first saw them, I said, oh, wow, how'd they come up with that? So you have this powerful hammer called constrained optimization. We have these tricky little constraints we have to put in. How can we use this tool? How can we modify it? How can we trick it? And it's really clever. So what you do is just think of a big number, a really big number, bigger than the maximum cookies that Half-Baked can make. And so I just wrote down 5,000. It's kind of arbitrary, not really thinking too hard. It's like we never make more than 5,000 cookies, so 5,000 pounds of cookies. So let's just pull out 5,000. And we never have a big number. How many max cakes do we ever make? Well, in the whole history of Half-Baked Bakery, we've never made more than 2,000 pounds of cake. Okay, so let's just pull down those two numbers. It's kind of arbitrary. Okay? It could be, if you have some consumer demand information, you might want to put that in instead. But, this is fine. Just got to get a big number, right? Kind of blows your mind. Just get a big number that you'll never, ever have to actually use. That's never becomes a binding constraint. And then you just add two new constraints, and these are called the linkage constraints. You say x is less than or equal to 5,000 times f of x, right? F of x is binary, 0 and 1, and y is less than or equal to 2,000 f of y. Oops, sorry, that should be an f of y there. Oh, goodness me. Okay, don't want anybody to get upset. Okay, and flip screen. Okay, 2,000 f of y. Okay, so what does that do for us, right? How does that help anything? Well, if you look at the linkage constraint, x is less than or equal to 5,000 f of x for cookies. You say, well, what happens if f of x is 1? Well, you just have x is less than or equal to 5,000, but that's non-binding because 5,000 is a really, really huge number that you never, ever have to worry about. How about if f of x equals 0? Well, then it's binding. If f of x is equal to 0, it crunches x down to 0. It forces the amount of cookies you make to be 0. Okay, so that's binding. How about if you flip it? If x is bigger than 0, then f of x has to be 1, right? If x is 0.1, then f of x will have to be 1. And if x is 0, right, we're not going to make any cookies. Well, what does solver do? It's trying to maximize profits. We're not making any cookies. There's no benefit to pay for setup costs for cookies, and so f of x will be equal to 0. So it figures this stuff out, right? And same thing for the linkage constraint for cake. Y is less than or equal to 2,000 f of y. So if f of y is equal to 1, then we're allowing y to go from 0 to 2,000. So that's not going to be binding because we never make 2,000 pounds of cake. If f of y is equal to 0, then we're forcing y to 0. You force it to crunch down. If we don't want to pay the fixed costs, we don't want to do the setup for cake, then we're not going to make any cake, sorry. If f of y is bigger than 0, if y is bigger than 0, well, the only way that can happen is if f of y is equal to 1. If y is equal to 0, again, if y is equal to 0, we don't make any cake. We're not getting any benefit. We don't want to do the setup. We don't want the fixed costs. So f of y will be equal to 0. So that's way cool the way the logic works on that. And so one note about solver, what we do mathematically or as algebra isn't necessarily what solver likes. So mathematically, we like x is less than or equal to 5,000 f of x. Okay, that's perfectly 100% okay. All your teachers back in junior high school, when you took your algebra class, would say, hey, full credit, you did it. But in solver, it will go ding. It doesn't make any sense. In solver, we have to have all the constants on the right-hand side. So we can't have a variable on the right-hand side. We got to get all the variables on the left-hand side. And so we just subtracted off. In solver, we write in x minus 5,000, f of x is less than or equal to 0. Okay, so that's the way we have to put it in solver, which is, kind of funky. It makes it look kind of strange, but that's just the way it is. So let me go back to my Excel file, and let's just see it put those in, right? So this is the same thing as we had, but we have linkage for X, and it's going to be 1 minus 5,000, and that's going to be less than or equal to 0. And then the linkage for Y, 1 minus 2,000 is less than or equal to 0. Okay. Again, these guys are just there for looks alone. And then we just have to copy and paste this down. And as always, just make sure that you did that correctly, right? 400 times 0, 300 times 1, 0 times 0, 0 times minus 2,000. Now let's go back. This is a bad solution, right? It doesn't quite work. Let's go back to a correct solution. Let's say where we make 0 cookies and 0 cake. Okay. We make no money, don't produce anything, don't have any fixed costs, right? If I just make 1 pound of cake, I'm going to lose money. Oh, because I have the 1 here, right? You have the fixed costs, you're going to lose money. But, I don't want to make anything. Just start at the origin. Nice and simple. Now, what I have to do is pull up this solver again. And again, just to go over it, my profit is F3. My cells are B2 through E2. I have binary constraints on D2 through E2, right? F of X and Fy are binary. And then I have these constraints. This is the production capacity constraints, right? Baking, mixing, icing. And what I have to do here is add in the linkage constraints. So I say add, and I want to put in the linkage constraints. Boom, boom. And then constants. Constants are 0. You say okay. And now we're set and ready to go, right? Always a little bit nervous at this point. Kind of, yeah, we want these to be 0. That's fine. Have this solution method. I think in solver, if you do LP simplex, it'll work too. Don't know why it shouldn't. And you hit solve. Okay, what happens? We got a happy days. Solver found a solution. Always a good sign. All constraints are optimally and optimality conditions are satisfied. All right. And it tells you a little warning here. The GRG engine is used. Solver has found at least a local optimal solution, right? With nonlinear kind of functions, they might be going up and down, and you might end up with a local max, but not the global max. And so it gives you that warning. If you use simplex LP, then you're guaranteed that's global. Okay, so let's just say, okay, gotcha. And the solution at the end of the day is we're making 700 pounds of cookies. We're not making any cake whatsoever. We pick up the fixed cost of cookies. We don't pick up the fixed cost of cake. And so our optimal profit is 700 times 0.2 minus 1 times 30, and that gives me 110. And then down here, we find that mixing is binding. We're using all of our mixing. Baking is slack, okay, or non-binding. Okay, practicing my typing. And the amount of slack is what? Is 250 minus 175. Okay. And then down here, of course, if we don't make any cake, we're not doing any icing, so that's non-binding. Right? If this is a forever solution instead of a daily solution, hey, we're going to get rid of the people who do icing. Oh, I'm sorry, not get rid of them. We're going to reallocate the people who do icing to other tasks or free them up to add more value to the economy elsewhere. Okay, and so here's a linkage constraint. Okay, this is non-binding. Okay, it's not being enforced, but my linkage constraint for Y is binding. Okay, for cakes, it's binding. Because I'm making 0 cakes, it's forcing the fixed cost to 0, and so that's become binding. With the linkage for X, we're going to make cookies, so we're going to pick up the fixed cost. But the thing is, the 5,000 is sufficiently big that it's not going to bind us anymore. It's not going to cause us any problems. We're just going to make as many cookies as we want, and here is 700 cookies. Okay, so that is just so way cool. I just really like that. All right, so yeah, awesome stuff. What you can do, I mean, really, this whole very simple, but so many really smart people have been looking at this for so many years that they've come up with all kinds of different, tricks to do when you have special situations. Okay. All right. Okay, so we put those constraints in. Again, this is the model. Just to say one more time how you set up the dialog box. Objective is profits. Maximize profits. Got it? Okay. Minimize cost. Maximize profits. The decision variables are B2 through E2, just like before. We have a binary constraint on D2 and E2 for the fixed cost. We have our production constraints, which are down here in rows 6, 7, and 8. That's 6, 7, and 8. And then we have the linkage constraints for cookies and cakes, and that's on rows 9 and 10. So F9, F10, and G9 and G10. I use nonlinear, GRG nonlinear, and set solve. And that's how the solution came about. Okay, so just a recap. Okay, without fixed costs, we'd go and make 400 pounds of cookies, 300 pounds of cake for a profit of $170. Okay, but that's misleading if you actually do have fixed costs, right? If you ignored the fixed cost, you're hurting yourself. So with fixed costs, we're going to make 700 pounds of cookies, and we're going to make a profit of $110. Right? The cost, we shift all of our productions to cookies. We no longer make any cake, right? So what happens? Apparently, customers don't like cake enough that they're willing to pay extra for it, right? They say, hey, cake, if I had to pay for your fixed costs and everything else, it's not worthwhile. You're not, and so you say, hey, I'm not making enough money on cake to justify its fixed cost and all the baking time it takes and all the icing it takes and everything else. I'll just make these cookies. Okay, cookies are simple to make. Any third grader can make a batch of chocolate chip cookies and they'll be delicious. So customers do not like cake well enough to pay for it. And so we just make cookies. So even though this seems like this business analytics is a very narrow technical field, you actually end up with strategic behavior, right? You have to think about, you're getting down to dollars and cents and what's optimal to do, but you actually end up with some qualitatively different behavior depending on what the situation is. And this is why it's so important to make your model as close to reality as you can. Some things you can ignore, other things you can't. Here we have significant fixed cost. If you ignore them, you're going to hurt yourself. When you put them in, you'll be doing something much different than what you thought you would have been done before. Okay, and so that's it. So this is the end of the series for optimization. I hope you enjoyed it. Please give me a thumbs up if you can, and I'll see you in the future. Bye now.